a stupid meme here, but it's to help you remember Avogadro's number. We're going to use Avogadro's number to start to get some ideas of what we're doing in the lab space and connect them to what we're talking about in the classroom. So the calculations of these are to again relate what we're talking about when we write out a chemical reaction and what you would measure out in a lab. The idea here is you have certain reactants and then you have the products. So you have, for example, an analogy here is the football team. You have all of the right pieces to get the end result that you want. And you need to make sure that you have 11 players on both sides. You have a football. You have all the right things that you need in order to make this happen. Here we are. We have our team that's going to connect here. We have a hydrogen molecule, and we have oxygen elements, and we're going to generate H2O. We're going to make water. We can say we have a molecule of this, atom of that, and we make a molecule of this, or for every mole of molecular hydrogen, we need a mole of oxygen to get a mole of water out. So how many moles of nitrogen and oxygen do we need to make 1 mole of N2O5? So let's start with this thing. So we look at equivalency. When we were talking earlier in the semester about looking at these and doing accounting for the different elements. So this is a pretty simple one, right? Nitrogen, there's 2 nitrogen atoms in this molecule and 5 oxygen atoms in this molecule. We have to have this ratio. So for every 2 moles of nitrogen or 2 atoms of nitrogen in this molecule, we have 1 mole of that molecule. So there's an equivalency. What the other equivalency we have is for every 5 moles of oxygen, we can generate 1 mole of N2O5. So this dinitrogen pentoxide, these equivalencies are also conversion factors. We can make 1 more conversion factor. 2 moles of nitrogen can combine with 5 moles of oxygen to form dinitrogen pentoxide. So these are equivalencies. We can use those as conversion factors when the appropriate time comes. And I'm going to show you an example of doing exactly this. So the question here is how many moles of dinitrogen pentoxide can we make with 1 mole of nitrogen and 5 moles of oxygen? Okay, let's look at how to do this. So in order to solve this problem, what do we have? We have 1 mole of nitrogen, and we also have 5 moles of oxygen. So let's start with the moles of nitrogen. What can we use in order to convert this to the moles of dinitrogen pentoxide? Remember, on the last slide, we just talked about these equivalencies. So we want to use one of these 2 equivalencies to allow us to use this as a conversion factor to solve that problem. The one that is going to be the correct one that we're going to want to use. So we can do this, we'll do this in 2 steps. We'll check with both of these. The 1 mole of nitrogen and the 5 moles of oxygen. We'll do this separately. If we have 1 mole of nitrogen to start with, we know that for every 2 moles of nitrogen, we will be able to make 1 mole of the dinitrogen pentoxide. Right, that was on the last slide. That allows us to cancel out moles of nitrogen, and then we're able to get, we have 1/2 of a mole of dinitrogen pentoxide that can be made if we have 1 mole of nitrogen. Now let's look at this other piece of information we have to double check to see if this is the same answer. If we have 5 moles of oxygen, we can do the same thing when we have 5 moles of oxygen, right? Here, that number 5, we can generate 1 mole of N2O5. So that is actually going to be 1 mole of dinitrogen pentoxide, right? 5 divided by 5 is 1. So which is the correct answer? Well, this is the idea where we come now to think about what is the limiting reagent. Since we can't create any more of something, right? This is one of the fundamental principles that we were talking about with Dalton's theories. We can not create matter. So if we only have enough to make a half of a mole, we would say that this nitrogen is the limiting reagent, and it only allows us to make 1/2 of a mole. So that's the answer. We can't make a mole of N2O5 because we only have enough to make a half of a mole, according to this, because this is the limiting reagent. So this is an important idea. These are kind of some of the exercises we're going to start doing, and in order to look at how many moles of something we can create, we need to know the starting point, and we need to go through the starting point for all of the different possibilities. So with our reactants, so the starting materials, sometimes you're going to have to check both of them to make sure, and then look at the least amount that's going to be created to identify the limiting reagent and then what the actual amount you can create is. Sometimes this also might say perhaps 1 mole of nitrogen and oxygen in excess. So you're saying you have an unlimited amount of oxygen, you don't have to worry about it. And in that case, you would only have to look at one of the elements or one of the compounds to determine how much you would create. All right, so I want you to try this on your own. Here's another question, kind of the same idea, but I want you to set this up and determine what that limiting reagent is and how much you can actually create then. So post this in the discussion board, and I'm going to move to the next question. So pause here, do the problem, and then we'll move forward. All right, let's look at something a little more complicated here, and we're going to start with this problem talking about calcium phosphate. This can be found in kidney stones, and if a sample of a kidney stone was found to contain 0.864 moles of phosphorus, how many moles of calcium phosphate are in that sample? First, we need to identify phosphorus in here, and this one atom within that group is going to be the 0.864 moles. So that's what we have. So now we actually have to do some accounting. Calcium, we have 3. Remember, we have to multiply this through like a mathematical equation. So phosphorus, we have 2 of those. Oxygen, we have 8 of those. So these are going to provide us that ratio. We have a 3 to 1, 2 to 1, 8 to 1 if we're talking about the calcium phosphate compound. In order to solve this, if I have this many moles of phosphorus, I will have to say for every 2 moles of phosphorus, I can create 1 mole of calcium phosphate. Get this out of the way. So that should make sense because, again, we have, if we multiply that through, we'll have 2 of these atoms of phosphorus in every 1 molecule of calcium phosphate. And that translates the same as 1 mole of calcium phosphate is equal to 2 moles of phosphorus. So then we have this conversion factor. I put this moles of phosphorus on the bottom so I could cancel that out. So the answer is half of 0.864 moles, which would be 0.432 moles of calcium phosphate. So now what I want you to do is to calculate the number of moles of calcium in 2.53 moles of calcium phosphate. So it's your turn. Pause here, post your answer on weekly content discussion board. So the easy part is going from the moles of one compound in a molecule or one element in a molecule to the number of moles of molecules or another number of moles in that system. So moles to moles are pretty easy. But now we're going to start looking at, in the lab, we're going to measure things out in grams. And then we have to convert to moles and then maybe back to grams. So this gets a little more complicated. This is where the factor label method system really comes into play for setting these problems up and making this process easier to work with. So let's just talk about this by using a problem as an example. The question is, how many grams of iron are required to use up all of 25.6 grams of oxygen atoms to form iron oxide? So this is what happens when iron rusts. Oxygen is present, and that forms this iron oxide compound. So we're going to use a full 25.6 grams of oxygen. First step is, what do we need to know about the elements that we're looking at? So let's start with what we have. We know we have 25.6 grams of oxygen. And we also know that we have this compound is going to be created. How many grams of iron are we going to have? So what we cannot do is say that every 3 grams of oxygen is equivalent to 2 grams of iron. This does not work for grams. No, we need to go through moles. So what we need to do is we need to determine how many moles 25.6 grams of oxygen weighs. So fortunately, we have periodic tables that help us determine that. And I'm going to estimate here. I'm not going to do 15.99. I'm just going to round up, just for this example, to simplify things. I'm going to round up to 16. So I know that 16 grams of oxygen is equivalent to 1 mole of oxygen. So I notice how I have oxygen here. This is helpful to have that kind of secondary part of the unit in order to keep track between iron, moles of iron, and grams of iron, and moles of oxygen versus grams of oxygen versus iron oxide. So this conversion factor, right, using the atomic mass of oxygen, we're able to, that number tells us how many grams per mole. And I can flip that because these conversion factors are equal to 1, and it doesn't matter if the numerator is in the denominator or denominator is in the numerator. Those things can flip if we're doing this to cancel things out for equations. So grams of oxygen, that goes away. So now I have moles of oxygen, and now I can look at these equivalencies, and I can do moles. I can use moles to relate these ratios here. So I'm going to want to cancel out oxygen, which is currently on the top, moles of oxygen. If I have 3 moles of oxygen from this number right here, I know that I will have to have 2 moles of iron. This is the ratio we can use to then cancel out moles of oxygen. Well, remember what we want is grams of iron. So I'm not there yet. Now I'm going to have to go back to our periodic table, look up the atomic mass for iron to generate that last conversion factor. The atomic mass for iron is 55.84 grams of iron per 1 mole of iron. Now I did it that way so my iron cancels out. 55.84 grams of iron is equivalent to 1 mole of iron. Remember, this number is the same as the atomic mass for iron. Now I've canceled out all of my units, and I'm left with the unit I want, which is grams of iron, right? That is what I want. So we multiply this through. That should give me the 59.6 grams of iron. All right, so in the book The Martian, or there's now a movie The Martian. So it's about this astronaut. They go to Mars to try to think about terraforming the environment. There's an accident, and it's a pretty interesting story. But in that story, our character is trying to take the rocket fuel, which is called hydrazine. He wants to use this to generate hydrogen, and he's going to decompose the hydrazine to hydrogen gas. And this is the chemical reaction. The hydrazine will decompose to nitrogen gas and 2 parts hydrogen, molecular hydrogen. So I would like you to look at and try to solve this problem. How many grams of molecular hydrogen are going to form during the decomposition of 32 grams of hydrazine? So I'd like you to put that together, post that in the discussion board, and then we'll go from there. So this was an interesting thing that happened in the book or in the movie, where there was actually an explosion because he talks about this chemical reaction, and he did this wrong. He did this calculation incorrectly, and he ended up with more hydrogen gas than he thought. Probably, or potentially, I don't know. They don't talk about what the error was, but maybe he was assuming there was 1 molecule of hydrogen instead of 2. I'm not sure. Maybe this wasn't balanced or something. But anyway, that's part of the story here. That's interesting. Finally, we want to talk about this percent composition. So it's a way to determine and get a relative abundance of a compound in a group. And we're going to talk about why this happens in just a moment, but it's basically a list of percentages that should equal 100% in the end. And it just gives you the relative abundance of that element within a certain compound. So here's an example, is sodium carbonate, and we want to determine the percent of each atom within that element. Now remember, when we have these numbers, this is 2 atoms of sodium in every element, and 1 atom of carbon and 3 atoms of oxygen, or we can say moles. We can say 2 moles within this group if we have a mole of this compound, or 1 mole of carbon in this 1 mole of this compound. So we're going to have to think about those ratios and then convert that and figure out what the masses are. So how we do this to determine the percentage of each atom, we have to look and have some information about the atomic masses. So for this whole compound, the atomic mass for sodium is 46 grams per mole. And the molecular mass for sodium carbonate is 106 grams per mole. So we will take this value and divide it by the atomic mass for the sodium carbonate multiplied by 100, and then we're going to get our percentages. And so you're basically saying out of every 106 grams, 46 grams of that is sodium. So how did we get this 46 number? Sodium, the atomic mass for sodium is approximately 23 grams per mole. And in this compound, there are 2 of these, so we took this times 2 to get 46. We have 1 carbon, and carbon's atomic mass is approximately 12. And then oxygen's atomic mass is approximately 16 times 3 is 48. So these are these numbers. And then we add those all up, and that 48 plus 46 plus 12, that's how we get the 16. So now we have these numbers. We're going to take these masses of that account for sodium versus carbon versus oxygen. We take these values and divide them by the total molecular mass, which is 106. Multiply that by 100, and we'll get 43.38% sodium, 11.33% carbon, and 45.29% oxygen. And now if we add these together, they should give us pretty close to 100%. There might be some slight rounding errors, but that should be close to 100%. This again is a way to specify the relative abundance of certain elements within a compound. And this is useful because when we start to look at, when we start to look at and try to identify different compounds, this is a chemistry thing, right? It's when we're initially trying to solve problems and understand what is in a compound or in a solution, one of the first things that you might want to do is take that molecule, break it down into its elements, and then we're able to determine the percent composition of different atoms within the element using, for example, a mass spectrometer. So that's one of the first steps in kind of the investigation of identifying what the matter is that you're working with. So this is a good place to stop, and we're going to start with the next chapter, the next part of this chapter. We're going to use the percent composition idea to start thinking about other things we can do with this. We're going to continue to use the factor label method system to solve more and different types of problems.